Hey, Kelly here, and this example is going to walk you through calculating a standard cell potential of a voltaic cell. Now we're interested in which combination of this silver and tin system, like which one is oxidized, which one's reduced, so that we can get a spontaneous reaction. We need a positive E cell, positive voltage. Now, the way you want to do that, if you're given just a table of these, half reaction cell potentials, is first identify the reactions you're interested in. So we are working with this silver combination and the tin combination. So we have silver here and tin. So find them on the list. Now, this is just an abbreviated list. You might get a different version in different textbooks, different internet websites. This first guy is our silver, right? And then down here is our tin. So what I'm going to do first is just write them out, so bring them out of the table, just so we can look at them a little bit, hopefully clearer. So we have our silver plus an electron goes to your solid, and you have its own cell potential of 0.8 volts. And then we also have the tin. We have tin, I'm just going to write it as is, plus 2 electrons goes to tin solid. And it has its own cell potential as negative 0.14. So they're all written as reductions. We can't add two reductions together to get an overall spontaneous reaction. We need to pick one that is being oxidized, okay? Now, there's kind of potentially a few ways you can think about it. The way that personally works for me is I look at their own cell potentials on their own, these two values. If we added the two reactions and one was oxidized and one was reduced, we'd want the maximum cell voltage possible that is positive. Now, you can reverse the silver, which would make the cell potential a negative 0.8, or you can reverse the tin. Now I'm seeing that I would reverse the negative to make it a positive value, because when you add them together, you get an even more positive value. So what does that mean with the reaction? That means we're going to reverse the tin reaction. So I'm going to reverse it. Tin solid goes to the ion. And what does that do to the cell potential? It changes the sign to a positive. So in that regard, I would want to call the silver as the reduction. So this is the reduction half reaction, and the tin is the oxidized. Okay, that is ridiculous. Let's try that again. Oxidized reaction. If we add them together, let's just bring them down here one more time. So the reduction reaction is the silver plus an electron goes to silver, where your E naught is 0.8. And then your oxidation, so I'm going to rewrite this down here correct, goes to the tin 2 plus 2 electrons, and its E cell is positive. So now we can kind of clearly see it a bit more. You'll notice that technically, to write the overall cell reaction, the electrons are not balanced. So we would want to look at that and say there's 2 here on the tin and there's only 1 in the silver. So we do need to balance this reaction up here. I'm just going to go ahead and rewrite this a little bit spaced out. So we have plus 2 electrons right there, okay, and then 2 solid silvers. So that would allow us to actually write the balanced equation. And remember, when you add coefficients to these half reactions, you do not do the same. You don't multiply the cell voltage by that amount. Those are not related. So you have 2 silver plus, if we're adding these together, plus a tin goes to 2 silver solids, plus your ion for the tin. I'm not writing out the electrons because those will cancel. And to actually do the math here, to find the overall E cell, we're going to add together the 0.8 volts plus the 0.14 volts, because we literally added the reactions together. 0.94 volts would be your actual standard cell potential. So this is the way that kind of I was taught, and it makes more sense to me personally. But you can, technically do it one other way that I'm familiar with, at least. And we can write our E cell reaction as the reduction minus the oxidation. And if you do that, you have to just clearly understand what you're extracting from the table. So in this particular case, the reduction reaction would be the 0.8 minus the oxidation. And at that point, you just type in the actual voltage that you see on the table. And you'll notice you get to the same answer. But I've noticed many times this confuses people because they don't know if they're switching signs and whatnot. It's probably confusing because we're showing you two different ways of doing the problem. But suffice it to say, I kind of like the logical way of adding two reactions together that complement each other. One is oxidized, one is reduced, and then you're adding the voltages. But you need to remember to switch the sign. So take your pick as far as which way you decide to approach these problems, but just make sure you're consistent and keep practicing these problems because they will just keep on coming.